Now the next thing that kind of connects together with the idea of exponential functions is something called compound interest. Now this happens when like money is invested and interest is paid on into that money, and then when interest is paid again, it's given as a percentage of how much money is there. So basically what happens is, like in a savings account, you might get 1% interest paid. That 1% interest goes into the account, and then the next time interest is paid for 1%, it's calculated on the original amount of money plus any interest that's already been earned. So that's what we call it compounding, because it compounds upon itself every time that interest is paid. And so there's a formula for this. It goes A equals P times 1 plus R over N raised to the NT power. Okay, what these letters stand for, P stands for principal. Now principal means this is the initial amount of money which is invested. And let's just say like a savings account or something like that. So that's the initial amount. R stands for the interest rate. This is how much is being earned in interest. And the thing to make sure to know about the interest rate is when we use it in a calculation, it needs to be in a decimal. Usually interest rate is given as a percentage, but we always change it into a decimal before we use it. Okay, T stands for time, and usually time is going to be stated in years. So the amount of time where all the interest has been earned, 5 years, 6 years, things like that. Okay, N in this formula stands for the number of times compounded per year. Now what we mean by compounded is paid. How many times interest is paid out per year. Okay. And then finally the letter A in this formula, that's going to stand for the amount of money after so many years. T years, in fact. So this is kind of the setup here. We have a principal, initial amount invested, an interest rate, which says how much interest is paid for so many times per year, the number of times, which is the letter N, and then T will be the number of years that this investment goes on. Okay, so this is one way of doing compound interest. There's another way called continuous compounding. Now, continuous compounding means that it's constantly earning interest. There's no breaks in the time between when interest is being paid. So in this case, there's no letter N involved with this formula. It just says A equals P E raised to the RT power. So no N number to have to worry about here, because the interest is always being paid, so that we don't have to think about it being broken up into paid at different times during the year. It's always going to be earning interest. So those are the two formulas that we have. Okay, one has the N, one does not, but both are going to have P, R, and T at least involved with it. Principal, interest rate, and time. So what we're going to do now is figure out the amount of money that'll be there after so many years with a particular kind of investment. In this one it says the investment is $10,000 for 5 years at an interest rate of 5.5%. Now the first one says we're going to compute the amount when the interest is compounded semi-annually. So when it says compounded semi-annually, that tells us how many times per year the interest is being paid out. And semi-annually means 2 times per year. So we're going to use that information now to figure out the interest and the money and everything put together. So let's start out with the letters in our formula, starting with P. Again, P stands for principal. That's the initial amount invested, $10,000. T stands for time. In this case would be 5 years, so T is 5. The interest rate, now it says here 5.5%, so we need to change that into a decimal. So as a decimal, 5.5% is 0.055. What we do to figure out the decimal from the percentage is move the decimal point 2 spaces over to the left, and that takes it from the percentage, 5.5%, over to the decimal of 0.055. So that's what we're going to use for R. Interest rate, 0.055. Okay, so that gives us P, T, and R. N, again, stands for the number of times that it's compounded per year. And so since it's a semi-annually, we say it's twice per year, N would be 2. So we need to put this into the formula so we can calculate the amount. So just looking at the formula, putting each number where it's supposed to go would look something like this. Now this has a lot of numbers and a lot of calculations going on, so what I'm going to do is just use the calculator to help me calculate this out. So let me get the calculator here pulled up so we can all put this in. We'll start by putting it in pretty much exactly like it shows. We can put 10,000 and then we'll put open parentheses 1 plus 0.055 divided by 2, then put close parenthesis. Now again, we need to put the exponent thing up above all this, which is that little arrow pointing up. So when I put right here above the division and below clear, we push that button, it allows me to put what should be up in the exponent. So this is to the 2 times 5 power. So this should be exactly what we have down for our formula. And when we hit enter here, we'll get this much money here. Now, a thing to keep in mind is we want to round this off to the nearest cent, basically, so the nearest hundredths place. So let's put this over here, and let's look at the number that we got. So when I round this off to the nearest cent, it'll be approximately $13,116.51. So from $10,000 to over $13,000. That's how much money is going to be there after the interest has been paid semi-annually for 5 years. Now let's do this for a slightly different way. Let's do this for quarterly. So how many times a year would quarterly be? Indeed, that would be 4 times. So for us, n is equal to 4 versus 2 as we did in the last one. So when we do this in the formula, more or less it's going to look exactly the same. We'll be just using the number 4 instead of the number 2 for n. Now if you'd like to practice doing this on your own, if you have the calculator handy, you can work this out, and I'll come back in just a second if you want to pause the video here and show you what I got for calculating the interest. So I came out with approximately, again rounded to the nearest cent, $13,140.67. Now we can continue to increase the number of times compounded, going all the way up to monthly, which in that case we're talking about now 12 times a year. And in that case, n would be 12. And so let's do the calculation and see if it really makes a big difference in the amount of money. So using the formula again, but putting the number 12 for n looks something like this. And if you'd like to calculate this for practice, see what you'd get from calculating it for compounded monthly. I came out with $13,157.04. So as you can see, as we're going along here, there's not a big jump in the amount of money earned. There's some point at which the amount is really not going to be going up by too much more. In fact, we could go up all the way to continuously. And so that means it's not monthly, it's not quarterly, daily, hourly, it's always earning interest. But when we do continuously compounded interest, we had to use the other formula instead. A equals P e to the RT. So in this case, all we'll have to do is plug in for P, 10,000, then E raised to the R times T power. So it'll look something like this. Now let me show you all how to calculate this with the E and all that stuff going on. So to do this in the calculator, we'll start off with the 10,000. Then again, we have to press second, and then the LN button to get to the E. And now all we need to do is put that stuff, it's already got it up there in the exponent. So interest rate times time. And when we hit enter, that now tells us how much approximately it'll be. And we'll again round to the nearest cent. So here's what we're looking at. Approximately 13,000, still just $13,165.31. We'll round that to 31. So as you can see now, when we went from from monthly all the way up to continuously, it didn't increase by a huge amount either. But this would be the maximum amount that could be earned via compound interest with this interest rate and this amount of time. Now for practice, here's a good example that you may want to kind of start working on your own. Pause the video here. It says we have $12,000 to invest. Which would be better and yield the greatest return over 3 years? 7% compounded monthly or 6.85% compounded continuously? So if you want to try to compute these using our formula, just take a second, see if you can get the formula started and do the calculation. And if you pause the video for a second, I'll come right back and work this one out. So what we're going to do here is start with the principal. That's the $12,000 to invest. Now, we do know the amount of time that we're dealing with here is 3 years, so that's going to be the letter T, T for time. So T is going to be 3. Now, for the first option, option 1, it's compounded monthly. So that's going to be, again, 12 times per year, and so n would be equal to 12. Also, the interest rate, it says, is 7%. So we change that into a decimal, that'd be 0.07. So R is equal to 0.07 for the interest rate. Now we'll look back to our formula from a second ago. It looks something like this. We can plug in the numbers for the different variables. 12,000 times 1 plus 0.07 divided by 12, all raised to the 12 times 3 power. Now if we do the calculation here for this one, we get out approximately $14,795.11. So that's option 1 with compounding monthly. If we go to option 2, that's going to be continuously. So again, continuously, we need to use a different formula, PE to the RT. It also tells us a different interest rate for this one. It's a lower interest rate of only 6.85%. So if we change that into a decimal, 6.85% would go 0.0685. So R would be 0.0685. Now if we plug that into our formula for continuously compounding interest, we'll put 12,000 e to the 0.0685 times 3. And that's what we have to use the calculator in order to get an approximation for. What I came out with is approximately $14,737.67 when rounded to the nearest cent. So of these two, we can see which one is actually bigger. Option number 1, that's compounded fewer times but has a higher interest rate, would be better. So that shows you how the different interest rates and compounding can interact in order to produce more or less interest as a result.